So a little bit of on DC motors. The background before the widespread use of power electronic rectifiers and inverters, or power electronic converters in general, DC motors were unexcelled in speed control applications. Today, however, with induction motors with solid-state drive packages are a preferred choice over DC motors. So one first definition in DC motors would be their speed regulation. So the speed regulation in DC motors is defined at the omega, or the speed at no load, minus the omega at full load over the omega at full load times 100 to make it in percent. So we have two conditions. One is the no load condition, where the motor has its most basically speed. And then we have the full load conditions where the speed of the motor is decreased. So the closer these two are together, it means that speed regulation would be closer to zero, right? If it is closer to zero, it means that we have a better motor in the sense of it doesn't get impacted by the load very much in terms of the speed that it can provide. We can also describe that using the RPM. So omega is the standard radians per second based on SI. And then another unit that is widely used is RPM, revolutions per minute. There are 5 types of DC motors: a separately excited, shunt DC, permanent magnet, series DC, and compounded DC motors. All right. So this is showing the general equivalent circuit of a DC motor. So we have two basically circuits, or we should have two circuits. One is associated with the excitation system, which you have an RF and LF. LF is the equivalent inductance, which in the DC conditions does not get involved in the circuit calculations, as you know. But RF can get in series with an adjustable resistance in order to control the speed of the motor. So that R adjusted plus RF can sometimes be represented as a variable RF, which is the resistance inside the excitation circuit that we can use in order to control the motor. What we showed last time, as on the stator side, we assumed that we had an N pole and S pole, and it was constant kind of, it was like a permanent magnet. In most applications, we don't have that permanent magnet. We really need to provide that north and south poles through an excitation circuit. And this is the representation of the excitation circuit in here. All right, now let's look at the armature circuit. In the armature circuit, we have the armature itself, which can be represented as basically the source. And then we have the brush equivalent, has some voltage drop across it due to commutation that we just explained last time. And then we have an equivalent resistance in the armature circuit, which all these together can be represented as an RA, resistance, equivalent resistance in the armature, and a source. Okay. In other words, sometimes we can just ignore this brush if it is small enough. Now, we had two major equations in the DC machines. One was associated with the voltage induced in the DC machines, which was a function of the flux per pole, the speed of the machine, and a constant, which depended on how we construct the machine, how many basically conductors we have, how many coils we have, how many conductors per coil, how many parallel circuits, and so on and so forth. So that K would be determined. Also, for the torque that is induced in the machine, that we call it the electromagnetic torque, or induced torque, we have a representation of tau is equal to K times phi times IA. So still, we are dependent on the flux per pole in the machine to determine how much flux, how much torque can be induced. And we are also dependent on the armature current, how much current we have in the armature. The same K applies in here. So these are the same K values for both the EA and tau induced. All right, now, in general, we have a magnetization curve for the machine. This magnetization curve has a linear region where we have basically the dependency of phi versus F. F is the magnetomotive force, right? Magnetomotive force associated with the excitation circuit, and how much it could produce phi, which is the flux in Webers. So in this linear region, there is a linear relationship between phi and F, but as F grows or increases, phi cannot keep up with the same rate, and it goes to a saturation. So in most applications, we are close to the knee point because we want to have the maximum flux possible and still not go to the saturation region because of the extra losses that could be produced in the machine because of that. So we want to be kept around the knee region. We can translate this phi versus f to an E versus IF basically equivalent. That has the same shape. So we know that E is K phi omega, right? So if you can keep the omega at the constant level, if you assume that omega doesn't change, the same relationship with a different scaling, obviously, would but the same basically pattern would exist between E versus IF, because IF is also equal to your F divided by the number of turns in the coil, right? So the same type of relationship is used as a magnetization curve of a DC machine expressed as a plot of EA versus IF for F fixed. Keep that in mind, that this has to be basically expressed in a certain speed. So this means that if the speed changes, then EA has to be scaled up and down proportionally with the same proportion. So we can use this, as we will see later in the examples of how to use this magnetization curve. Let's look at basically two of the concepts here. The first is the separately excited DC motor versus a shunt DC motor. So there's really nothing much different between these two. As you can see, the only difference is that in the shunt DC motor, we are combining the two circuits together to be provided through the same source. So this VT is the main source, the main terminal of the motor that we're providing the power through. So through the same source, both the field and the armature can be energized. Whereas in the separately excited DC machine, we have to have two different sources. So V terminal would be applied to the terminal of the motor on the armature, and VF would be provided. That's a separate, basically, DC source that would excite your excitation circuit. Okay. So in order to not use two different sources, we, in most applications, we really have this shunt combination or the shunt circuit associated with the shunt DC motor. But the equations, as you can see, are pretty straightforward. So here, IF in the excitation circuit would be equal to VF over RF. In the shunt version, we have VT over RF. Then VT for both cases, the separately excited and the shunt DC motor, would be EA plus RA times RA. The load, basically current, would be a little bit different. So in the shunt motor, as you can see, whatever load is basically drawn from the machine would be divided into two paths. The current would be divided into two paths. One is the armature, the other is the excitation circuit. However, the load current in the separately excited would be the same as the armature current, right? And then it would not, the IF would not be impacted by the load, in other words, because it has a separate circuit. Now, in most circumstances, we'll want to look into torque versus speed characteristic of a DC machine, which means that we want to see if we increase the induced torque that is coming out of the machine and compare and plot it versus the omega, the rotor's rotational speed, we want to see how it is going to vary. So in the case that you do not have any armature reaction, which means that you either compensated for the armature reaction through compensating windings, or in the cases that armature reaction is very small, then the speed versus the torque versus speed would be pretty much like a line, a decreasing line with a negative slope. But in the case that you have the armature reaction present, you will see that as you are increasing the tau, then for some time, you would have that linear relationship. But with increasing the torque, if you compare that with the case that there was no armature reaction, when you have armature reaction, your speed doesn't go down at the same slope that would be in the compared to the case that you didn't have any armature reaction. And that's because of the effect of flux weakening on the speed. When the flux weakens, we will see that the motor's speed will go up. Okay, so how is that possible? We had VT equal to EA plus RA times IA. Since the induced voltage, or EA, is K phi omega, so we just substitute K phi omega with EA. And since tau is equal to K phi IA, then IA, instead of IA, I can basically put its equivalent from this equation, tau over K phi, right? Now, this means that this equation 9.3 can now be expressed in terms of phi, tau, and that k constant of the machine, which gives you, basically, if you solve for omega through this equation, you get this. Okay. Now, if you look at this equation 9.7, you will see that if we assume that Vt and Ra are constant, k is also constant. Now, if you consider phi to be constant, which means that you're neglecting the armature reaction, then you have two constant coefficients in here, which explains why your omega m would be linear, its relationship with respect to tau induced, right? And a negative slope is because of this negative sign in here. But if you have armature reaction, and that armature reaction is really depending on how much current is flowing in your armature, the more the current flows in your armature, the more armature reaction you would have. And its impact is to reduce phi, right? If phi is reduced, you can see that this gets bigger, as well as this with a square factor. So therefore, you see that deviation from the line with armature reaction. And as you can see, its impact is because these two get bigger because of phi getting smaller, their impact would be to basically reduce the decreasing slope of the omega, if that makes sense. Now, let's look at one example in here. You have a 50 horsepower, 250 volts, 1200 revolutions per minute DC shunt motor with compensating windings. When it says with compensating windings, we have to keep in mind that it's no armature reaction. Has an armature resistance of 0.06, which includes basically the effect of brushes and everything. And its field circuit has a total resistance of RF plus R adjustable equal to 50 ohms. So this total is 50 ohms. This total is 0.06 ohms. We produce a no load speed of 1200 revolutions per minute. So when the motor is under no load conditions, we just energize it without any mechanical load on it. It can give us 1200 revolutions per minute. And there are 1200 turns per pole on the shunt field. So the number of turns on the shunt field is equal to 1200, looking at this figure. Now we want to see what will be the speed of this motor when its input current is 100 amps. Input current means this IL. When its input current becomes 200 amps, becomes 300 amps. So as we are increasing IL, or the load current, it means that we're putting more torque on the machine, right? So therefore, it would require more power from us, from the source. That IL increases, and that should result in decreasing the speed of the motor, right? When you put more load, it should decrease basically the speed. And we want to see how that decreasing is happening. And finally, we want to be able to plot the torque speed characteristic of this motor, okay? And we're assuming that there is no armature reaction in here, okay? Now let's go over this. I also have the MATLAB code provided for this example that we can go through that after we just read the descriptions in here. So solution. The internal generated voltage of the machine with its speed expressed in revolutions per minute was chi prime phi n. So EA was equal to chi, a constant, chi prime times phi times n. Now, since the field current in the machine is constant, why? Because we're assuming that the machine has compensating windings. As you can see through the circuit, Vt is also constant, and this field resistance is constant. So therefore, the current that flows in here is constant. And because there is no basically armature reaction, phi is also remains constant because phi has a relationship with IF. And since there is no armature reaction, the flux in this motor is constant. So overall, we can conclude that phi is constant. Then the relationship between the speeds and internal generated voltages under two different load conditions would be like EA2 over EA1 would be K prime phi N2 over K prime phi N1, right? So since both K prime and phi are constant, then we can conclude that basically N in the second condition would be equal to E in the second condition over E in the first condition times N1, right? Easy. So through here, we can now say that at no load, the armature current would be 0, right? If you have no load on the machine, it means that IA would be 0. So EA under no load conditions, which we call it EA1, would be the same as VT. So VT will provide some current through the excitation circuit, but does not provide any current in the armature because armature doesn't need it. There is no load on the armature. So EA1 would be equal to VT equal to 250 volts. While the speed N1 would be how much? Based on the problem statement, that's 1200. That's what the problem says. Under no load conditions, we're having a 1200 RPM. If you can calculate the internal generated voltage at any other load, then it would be possible to determine the motor speed at that load from this equation 9, right? Easy. Okay, so I'm just repeating the problem statement and the circuit here. In the first part of the problem, we had IL equal to 100 amps. So if IL is equal to 100 amps, IA would be IL minus IF, and IF would be VT over RF. So IA would be 95 amps. If there is 100 amps drawn by the motor, 95 amps goes to the armature, through which you can find out the EA. So EA would be 250 minus 95 times 0.06, right? So this gives EA equal to 244.3 volts. So through here, you can find N2, and in the second condition, from EA2 over EA1 times 1200, which means 1173 RPM. This is basically in the first case. In the second and third case, you can also find the speeds proportionally. As you can see, as EA gets smaller, you will see that the speed gets smaller too. So the speed decreases. You could also use the same concept and find the plot of the torque versus speed. So for plotting the torque versus speed, what you can do is to find out the torque from the P converted. So P converted is the power that is being given into this source in the motor circuit. So that would be EA times IA. That's what we call the P converted. And that would be equal to tau times omega, the induced torque times omega in the machine. From this equation, you can find tau. So at every loading condition, you can find EA, IA. You can find omega, like what we did here. You found N. Through N, you can find omega. And you can find tau. And then you can just plot tau based on your NM. So this process can be just repeated for all loading conditions. Let's look at this code briefly to see how it works. Also, some of these given information will not be sometimes used in the problems, but try to get used to basically what really needs to be used in the problem, what does not need. So, for example, 50 horsepower, we didn't really use that inside the problem. That's just part of the characteristics or properties of this machine that has been provided to us. So I'm just putting these VT N0, the speed at no load, RA, RF total, which is the sum of RF plus R adjusted based on the problem statement. And these are the three different loading conditions of the machine, 100, 200, and 300. We know that EA0 is equal to VT, which means EA under no load conditions. So for part A, you can find IA, EA, and N. Then IA, EA, N for the second case and third case. Now, in order to really plot that tau versus N, you can basically have a vector of IA from 0, which means no load, all the way up to, for example, 300 amps in steps of 1. And then you can find out your EA vector, which would be really your VT minus RA multiplied by IA vector. So if you look at here, if I run the code up to this point, you will see that for IA, you will receive basically a vector because you wanted it to go from 0 all the way up to 300 in steps of 1. So this is a vector of 301 numbers. And then if you really want to find EA based on that vector, considering the fact that VT and RA are constants, you should do that element-wise. So that's why I put that dot basically multiplied to give basically a vector here for EA as well. And then your N vector would be found. N vector would be just this EA vector divided by EA0 times N0. That gives you the N vector n at all of those points. And then based off of that, your tau would be found. Again, element-wise calculations. And then finally, you can plot tau versus n vector, which here it is. Right? So this is basically the plot. So let's go to the second example. So as you can see, really, the circuit-wise, the motor doesn't have any complex circuit. It's all based off of a bunch of resistances, a bunch of sources. That's it. The only thing that can make it a little bit complicated is the nonlinear operation of the machine when it goes into saturation, when it goes into the nonlinear curve of the machine, which we're going to do some examples in here. Example 9.2. Again, we have the same pretty much machine that we had in the previous example, without compensating windings now, which means that we should probably get into take into consideration the armature reaction. It has an armature resistance of 0.06. Filled circuit has a total resistance of 50 ohms, and it produces a no-load speed of 1200 RPM. So at no load, when there is no load, there is no armature reaction also. So that's why the same speed is applying, although this machine is like the previous machine, except that it doesn't have compensating windings, but at no load, it provides the same speed. There are 1200 turns per pole on the shunt field winding, and the armature reaction produces a demagnetizing magnetomotive force of 840 amps at a load current of 200 amps. So when the load current is at 200 amps, it produces an equivalent of 840 magnetomotive force, which works against the field MMF, basically. The magnetization curve of this machine is shown in figure 9.9. We want to find the speed of this motor when its input current is 200 amps. So we're providing 200 amps. We want to find out the speed of the motor. So the solution is that if the motor's current is 200 amps, which means IL is 200, then the armature current should be found at 195 amps, okay? Which means that your EA should be 238.3. Okay. Now, we should also consider the demagnetization magnetomotive force. So, although our IF, the current inside our magnetization circuit, is equal to 250 over 50, which is how much? 5 amps. But its effective value is not at 5 amps. It's as if some value needs to be subtracted from it. And that is equal to 840 divided by the number of turns, which gives you basically an IF star. So it's as if your machine is really working under a condition where its excitation current is 4.3 amps, not 5 amps. Does that make sense? That's because of the effect of your armature reaction. Now, let's look at the magnetization curve now. Looking at here. At that point, 4.3, this would result how much voltage? 233 volts. Okay, so if you look at this 4.3 amp, go all the way up, it produces 233. However, look at this curve. This curve is the magnetization curve of the machine. We mentioned that we usually give this curve at a specified speed in the machine. So in this case, this curve has been given at 1200 RPM, which means that at 1200 RPM, if you give it basically an equivalent 4.3, it would produce a 233. Now, we don't know what the speed of the machine is. So therefore, how would you find the speed of the machine? The speed of the machine would be really proportionally dependent on the difference in the EAs, in the armature, basically, voltage now. In other words, the speed that you're trying to look into versus the 1200 RPM, which is the initial speed or no load speed, would be the same as the ratio of EA over EA0. So let's go over this. We know that the internal generated voltage EA0 would be 233 volts at a speed of 1200 based on based on this curve. Since the actual internal generated voltage is how much now? Is 238. Then it would determine how the speed of the machine would be deviating from that 1200. The actual operating speed of the machine must be conforming to this. EA over EA0 would be N over N0. So N is what we're trying to reach into, and N0 is 1200. EA0 would be our 233, which we got it from the curve, and 238.3 is the one that we calculated in here under this particular loading conditions, which gives us a 1227 RPM as the speed of the machine. So this is the solution of part A. So in other words, the process that we went through is that we considered the IF, the effective IF in the machine, considering the armature reaction. Based off of that, through the curve, we found that that particular IF should produce this particular voltage. But this curve is given to us at a particular basically speed, which is 1200, which is a no-load speed of the machine. Now that we really have a 238.3 volt on the armature, how would that impact basically the speed? That would impact the speed proportional to the ratio of the EAs between the two cases. And that's usually what we need to do in many of these problems that deal with that nonlinear characteristic in the machine. All right, so part B is saying that this motor is essentially identical to the one in example 9.1, except for the absence of compensating windings, right? How does its speed compare to that of the previous motor at a load current of 200 amps? Okay, so in the previous problem, we found the speed of the motor at 200 amps to be 1144. It was 1144. But now it is equal to 1227. So the speed has increased. And that's what we mentioned is the effect of armature reaction. Because armature reaction reduces the effective phi in the machine, it will result in increasing the speed based on this equation. If phi is reduced due to armature reaction, then omega will increase. And that's what we just saw in this example. And in the third part, it's asking to calculate and plot the torque versus speed characteristic of this motor. We can do a similar process. So let me go over this MATLAB again. So that's the same machine, pretty much, except that we have the armature reaction. I'm also going to plot the curve. So this is a problem statement. I changed it a little bit to conform it to what we have. So in many cases, you do not have that plot. You don't have the means to basically find out the different E versus basically IF through the plot. You have to really interpolate. Assume that you have a bunch of points. And I've given that bunch of points here in this example. So this is basically the function that finds basically EA based on IF. So if you give it the IF, it will give out basically EA2. And these are the data points that have been provided. And we're going to interpolate. So whatever number we give as IF, it just looks at basically two values where that IF can fit within and comes up with a linear approximation to find. So I'm going to use that first to plot basically the curve. And this is the curve that is kind of similar to the curve that you had in here. Okay. Of course, it's not very well granulated because it just had a limited number of points. The more you give the points, the better it would be accurately determining that plot. So these are the same descriptions of the machine. The magnetization curve, the open circuit armature voltage versus the field current at 1200 RPM is described by the IFEA function below that I just went through. First, we want to plot the curve in the field current range of 0 up to 280 in 0.01 amp steps. And the motor is essentially identical to the one in example 9.1, except for the absence of compensating windings. Based on this, and assuming that the demagnetization magnetomotive force varies linearly with the load current, we want to find the speed of the motor when the input current is 100 200, 300, and then we want to plot the torque versus speed characteristics. So I made this kind of similar to the previous problem. I wanted to find out basically the speed at different operating points, and just to expand the problem to an actual plot of the torque versus speed characteristic as well, okay? So for that, I'm going to change the IF from 0 up to 10 in 0.01 amps based on the problem statement. Not just 10, not there is a mistake in here. 0 to 10. And then I put EA is equal to 0 first, and then I go and one by one go over that function to find the associated EA and then plot it. So this is the first part. I'm just plotting basically this curve. This curve. And then part A, we say that the armature reaction is linearly changing. So the more the armature current we have, or the more the load current we have, the more basically your armature reaction would. If it is 0, the armature current is 0, then it means that you don't have any armature reactions. It is equal to 840 amp turns at a load current of 200 amps. So we're going to use this for that linear approximation. So this means that in part A, if the input current of the machine is 100 amps, then the armature reaction effect should be 100 over 200. We have this FAR at 200 amps equal to 840, right? So therefore, we just consider half of it for the case that you have 100 amps. And then IF under 100 amps would be, this is the IF star, in other words. That would be the actual current in the excitation circuit minus the effect of the armature reaction at that particular point. The armature reaction would be equivalent to 420 amp turns. We need to divide that by the number of turns. So this would be the effect of the field current subtraction. So this is the actual field current. We need to subtract it from this value, which is the effect because of the armature reaction. But IA is calculated through IL minus VT over RF total. So still, the calculation of IA would not be impacted by the effect of armature reaction, if that makes sense. And then where we want to find our actual EA is basically VT minus RA times IA. Now, this EA1 is associated with N1 speed. But through this IF 100 amps, which is the effective, basically, excitation current through the curve, we find the speed to be equal to how much? 241. This is coming from the curve. We're calling the curve, okay? Now, we should use that proportion. So with respect to the 1200 case, this would be now the N1. This is exactly the same process that we did in here. So that's the same thing. Nothing strange. So we just repeat that for the case where we have 200, except that that coefficient is not used because we have the whole 200 amps. So the whole armature reaction comes into picture. Same process. For the third case where the load is 300, now we have to consider again this coefficient, 300 over 200, because the armature reaction was linearly changing. So this is the third case. And then this is the process that I've been considering basically for the torque versus speed. I'm changing the load from 10 to 380 amps in steps of 1, finding the armature reaction, which is based off of the 200 amps. You have to divide basically that, whatever the load current is, to find its impact. And then find the IF and the actual IF and the IA. And then I'm finding the speed through the same process and finding the tau. And I'm just basically finding the tau point by point in this loop. And then finally, I'm going to plot the tau versus the speed, which, as you can see, is growing. And that's because of the effect of the armature reaction. So if you want to just compare that with this, you see that this was declining when there was no armature reaction, but here we're going up because of the effect of armature reaction. And that has been basically explained plotted in the book as well. That's example 9.2, and this is basically the plot, which if you just compare it with this, it's the same plot essentially. So it starts going up all the way up to 1260, up to 1260, 70. The tau is changing from almost 0 up to around 600, up to 500. So I plotted for a few more points, but that's basically the same thing. So this is a shunt DC motor. The associated parameters are given in the code. The machine's magnetization curve at 1200 RPM is described by the IFEA function. Find the induced torque and the speed of the motor at full load, first without armature reaction, and then considering the armature reaction. Okay, so here are the inputs to the problem. This is the circuit, and these are the inputs. VT terminal voltage is 240 volts. Our F here is 75 ohms. Our A is 0.19 ohms, and rated in the machine is 1200 RPM. Our adjustable has been put equal to 175 ohms. And F, the number of turns, is 2700 in the shunt circuit. FAR max is 1000 ampere turns. And IL at full load, this current at full load is 110.96 amps. So the first part is just easy, finding IF. Since we know VT and our F plus our adjustable, we can find IF. The second part says, what is IA at full load? So the difference between IA and IL would be in the IF. And since IF is constant, so we can find IA at full load from IL at full load minus IF. So that's how you can find that IA at full load. Now, it's asking for the case that there is no armature reaction. What would be the IF star at no armature reaction? So when there is no armature reaction, IF star would be the same as IF, right? So this is the case that there is no armature reaction. VEA0 when there is no armature reaction from the curve. So you can find that through the IF EA function. You would need to put the IF, which would be the same as IF star. So you can put either IF star at no armature reaction or IF. This should give you that. Now, what would be the actual EA when there is no armature reaction? You have basically this current. You have this VT. So that would be VT
minus
RA times IA full load. Correct? This should give you the EA at when there is no armature reaction. Now, what would be the N full load when there is no armature reaction? So this EA0 happens at Tn rated, right? This EA happens at this speed. So the relationship between the two should be equal to Tn rated times EA no armature reaction divided by EA0 armature reaction, because full load over the rated should be the same as EA0, EA over EA0. Now, when there is armature reaction, so basically what we need to do is to find the IF star, which comes from IF minus this FAR divided by the number of turns, right? This is ampere turns over turns, that becomes ampere. So this becomes your IF star when you include the armature reaction. Now with that, you can use the same function, but with the new star value to determine EA0. when there is armature reaction. So that happens at the rated speed. Now, the actual EA when there is armature reaction is how much? That would be the same as EA when there is no armature reaction. So because you have the same basically armature current, same VT, so the same EA would be found. So that should be the same value. However, it impacts basically the speed. The speed would now come from, you can use this already. So this should be the AEA R over EA0R, if that makes sense. Shall we run the script? Okay, so let's take a look to see if the answers make sense. This is your IF. IA at full load. IF star when there is no armature reaction with respect to the case when there is armature reaction. So you can see that IF has reduced. This makes sense. EA0 when there was no armature reaction versus the time that there is armature reaction. That also makes sense. So EA in both cases should be the same. So here we have the N full load when there is no armature reaction is this much. And full load when there is armature reaction is this much. So it's increased. And this should make sense also, right? Because one of the effects of weak field weakening is that the speed increases. So let's submit. Yeah, for me, yeah, it got all the answers correctly.